I'm going to introduce the next speaker for today's webinar, who is Shingo Motoki, who is assistant professor at the Graduate School of Engineering Science at Osaka University. He received his PhD from Osaka University in 2018, and his research is focused on variational problems, thermal convection, and turbulent transport. And I believe that today he's going to talk about turbulence and thermal convection. So Shingo Motoki, you can go ahead.
Okay, so thank you for your introductions, and hello everyone, and or good morning, or in Japan, good evening, everyone. So my name is Shingo Motoki from Osaka, from Osaka University in Japan. So thank you very much for inviting me to this excellent webinar. And today I'd like to talk about the multi-scale steady solutions representing classical and ultimate scaling in thermal convection. And this is a collaboration with Professor Kawahara and Dr. Jiménez and my student, Mr. Kawano. Okay, let us consider the full layer between the two horizontal walls like this, and heated from below and cooled from above. So this is unstable stratification case. And as well known, this natural convection is characterized by the two non-dimensional parameters, the Rayleigh number and the Prandtl number. And the Rayleigh number represents the buoyancy effect on the flow and related to the Reynolds number like this. And here, the capital U represents the buoyancy-induced terminal velocity. Okay, and as Rayleigh number increases, the flow is more complicated, like this, and becomes a turbulent state eventually, representing the multi-scale flow and thermal structures. Okay, so the wall heat flux is corresponding to the total vertical heat flux, from the bottom to the top walls, could be quantified the Nusselt number. And one of the primary interests in the Rayleigh-Bénard problem is scaling loss of the Nusselt number with the Rayleigh number. And over half a century ago, two scaling laws have been predicted and discussed. One is 1/3 power law, referred to as classical scaling, and the other is a 1/2 power law, currently called the ultimate scaling. The classical scalings have been commonly observed at high Rayleigh number in a lot of experiments and numerical simulations like this. On the other hand, the ultimate scaling means that the wall heat flux is independent of the thermal diffusivity like this. So this is related with the Taylor's energy dissipation law via energy budget of thermal convection. So the Taylor's energy dissipation law implies that the energy dissipation rate is independent of kinematic viscosity of the fluid. So, but the ultimate scalings have been never observed in conventional Rayleigh-Bénard convection, except in, for instance, a wall-free convection or the thermal convection between rough walls. Okay? For the Rayleigh-Bénard problem, the rigorous upper bounds have been derived by using a variational method. And Doring and Constantin first derives this upper bounds, and then the lowest asymptotic upper bounds was obtained by Plasting and Castle. And these upper bounds exhibit the ultimate scaling like this. On the other hand, we have recently found the optimal states, maximizing the heat transfer under the constraint of the total entropy. And this optimal state also exhibits the ultimate scaling. And this ultimate scaling is quite close to the lowest upper bound here. However, the maximal heat transfer state does not satisfy the full Boussinesq equation. So there is no the Navier-Stokes equation with buoyancy force. So these solutions requires an additional body force other than the buoyancy force. Then we have to try to connect these optimal solutions of Euler-Lagrange equations for maximal heat transfer problem to the steady solutions of the Boussinesq equations for Rayleigh-Bénard problem using homotopy continuation methods from the body force to the buoyancy force. As you can see, the three-dimensional optimal states could be continuously connected to the three-dimensional state solutions of the Boussinesq equations. This lambda is equal to 0 represents the Boussinesq system here. And in this study, we focused on these three-dimensional state solutions. Okay, so we consider the solution to the Boussinesq equations with the following boundary conditions. That is a no slip and impermeable and consistent temperature difference between the walls and horizontally periodic condition. And we have tracked the three-dimensional state solutions up to high Rayleigh number using a Newton-Kirchhoff iteration. This is a Nusselt number as a function of the Rayleigh number, and the red line represents the three-dimensional steady solution. As you can see, that these three-dimensional steady solutions exhibit the classical scaling commonly observed the turbulent data rather than the ultimate scaling achieved by the upper bound or maximal heat transfer. Okay, so this is the mean temperature profiles and root mean square temperature in the three-dimensional state solutions and turbulent state. And the mean temperature profiles in the three-dimensional state solutions well follows that in the turbulent state like this. Furthermore, corresponding RMS values are good agreements with each other. Okay, let's normalize the distance to the wall Z by the thermal conduction layer thickness delta. So near the wall, so all temperature profile, normalized temperature profiles collapse onto a single curve. So the temperature difference exists only in the thermal conduction layer. And on the other hand, the RMS temperature exhibits the peaks at thickness delta. Okay, so we consider the physical mechanisms of classical scaling. And here we assume that the Prandtl number is of order of unity. And in the near wall regions corresponding to the thermal conduction layer, in the vertical component of the Navier-Stokes equations, advection and viscous and buoyancy terms can be comparable with each other. So this balance determines the length scale and velocity scale as follows. And this is a normalized vertical RMS vertical velocity by this velocity scale. We can confirm the vertical velocity fluctuation scales with this velocity scale. So, and the definition of the thermal conduction layer thickness here and this length scale suggests that classical scale. Okay, so let's look into the spatial structure of thermal convection. And these figures show the thermal and flow structures in the three-dimensional state solution and the turbulent states as the high Rayleigh number 10 to 7 here. And the yellow objects represents the ice surface of temperature, representing the high temperature plumes. And the gray objects represents the smallest scale vortex structures, visualized by the second invariant of the velocity gradient tensor. And near the wall, we can observe the sheet-like small-scale thermal plume structures with smallest scale vortex structures like this. And these smallest scale structures are quite similar to that observed in the snapshot of the turbulent state. And these small scale structures appears in the conduction layer, and the size of the thermal structures and the vortex structures scale with thickness delta, even in both three-dimensional state solutions and the turbulent state. So the three-dimensional state solutions reproduces the near-wall convective coherent structures in the turbulent state. But what then of bulk flow? So to examine the hierarchy of multi-scale vortices in the three-dimensional state solutions, we apply the coarse grinding to the velocity field. So coarse grind velocity U star is obtained by using a Gaussian low-pass filter. And here sigma represents the filter wise. And this method have been recently employed to capture the coherent structures of the wall turbulence. So this is a non-filtered structures, and the red ones represents the smallest scale vortex structures. And these blue objects represent the largest scale structures corresponding to the large scale circulation. And these structures are visualized by the positive Q of filtered velocity for the sigma is set to H. And for sigma is set to L over 4 and 8, L over 16 and 32. We can extract different scale vertical structures like this. And the red structure represents the smallest scale structures consistent with the non-filtered structure. And L over 32 corresponds to the twice the thermal boundary layer thickness. So, and the light blue objects and the green and the light red ones represent the intermediate scale structures. And we can observe these intermediate structures in the bulk region. And this is the one-dimensional energy spectra and energy flux in wave number space at the center of the fluid layer. And this is the Fourier coefficient in the two horizontal periodic directions. And the lateral and longitudinal axes are normalized by the kinematic viscosity and energy dissipation rate. And this eta represents the Kolmogorov microscale length. And the energy spectra of three-dimensional state solutions and the turbulent states are good agreement at high wave number regions. Furthermore, this energy spectra follows the Kolmogorov -5 scale power law with a constant 1.5. So this 1.5 constant is consistent is that observed in the inertial subrange of high random number turbulence. And in this intermediate range correspond to the from light blue to light red regions range here and here. So in this range, so the energy flux exhibits a positive value. That is, energy is from large scale to small scale, even in the three-dimensional state solution. And this energy flux scales with of orders of the energy dissipation rate in this region. Therefore, the three-dimensional state solutions will reproduces convective turbulence in bulk region. Okay, let's get back to the our original topics, that is the scaling laws in thermal convection. So in short, in the conventional Rayleigh-Bénard configurations, that is in the divergence-free velocity between the isothermal, no-slip, and impermeable and smooth walls, the maximal heat transfer state it can achieve the ultimate scaling. However, optimal state requires an external body force other than buoyancy. On the other hand, the three-dimensional state solutions and the turbulent states, of course, satisfy the full Boussinesq equations, but they exhibit the classical scale. So our next question is ultimate scaling achievable in wall-bounded buoyancy-driven convection? So in response to these simple naive questions, we have focused on this impermeable condition on the wall. So we have introduced wall permeability while keeping isothermal and no-slip condition. So these boundary conditions can be realized by the permeable wall. This permeable condition is a simple model mimicking a porous wall with a constant pressure plenum chamber underneath like this. On the permeable wall, the wall normal velocity is assumed to be proportional to the local pressure fluctuation. So here beta represents the permeability parameter. And for the beta is 0, impermeable condition is recovered. And on the other hand, the beta is infinity implies the wall free convection. Okay. So the governing equations are the same as the conventional Rayleigh-Bénard systems. The no additional body force and the no internal heating. So this thermal convection is characterized by the Rayleigh number, Prandtl number, and wall permeability. So the total energy budget has two additional terms, here and here. And this term represents pressure power on the permeable walls. And this term is strictly greater than zero. So this is always energy sink. On the other hand, this term represents outflow energy across the permeable walls. And this term's sign cannot be specified. However, we have numerically confirmed this term is positive in our computation. So please note that this thermal convection between permeable walls are sustained only by buoyancy power without any additional energy inputs. Finally, we will briefly introduce steady solutions and turbulent state in this system. Wall permeability significantly affects on the heat transfer in thermal convection. So the red line represents the three-dimensional state solution in the permeable case. We can observe the ultimate scaling at higher Rayleigh number. So the spatial structures clearly differ greatly between impermeable case and permeable case. So we can observe the remarkable large-scale thermal structure like this. And such a large-scale structure and strong large-scale circulation can be observed even in the turbulent state like this. And these high-temperature plumes fully extended from the bottom wall to the top walls through the bulk region. Okay, so in the turbulent thermal convection between permeable walls, we can observe the critical transition of heat transfer from classical scaling to the ultimate scaling. And this ultimate convective turbulence can be observed in the supercritical range at higher Rayleigh number here. Okay. And so in the impermeable case, we can observe the near-wall turbine structures corresponding to the small-scale thermal plumes, like this. And on the other hand, in the supercritical permeable case, the large-scale structures appears even in the vicinity of the wall. So these figures show the convection heat flux in the thermal conduction layer. And the bottom figures represent the buoyancy power spectra. And we can observe the significant buoyancy power at the small scale in the vicinity of the walls, leading to the small scale thermal plume structures in the impermeable case. On the other hand, in the supercritical permeable case, the energy spectra's peaks is located at the largest horizontal scale even in the near wall region. And this spectra suggests that these large-scale structures is generated by buoyancy. Okay, so even in the permeable case, the isothermal temperature condition is held. So the thermal boundary layer exists on the permeable walls, like this. On the other hand, the vertical transpiration velocity is induced on the permeable walls. But please note that the RMS vertical velocity is suppressed near the walls due to the presence of the wall. And RMS vertical velocity on the permeable walls scaled with capital U, so buoyancy-induced velocity in the supercritical region, where the ultimate scaling is achieved. And in the subcritical case, in the classical scale case, the RMS temperature in the bulk regions decreases relatively with respect to the delta T as Rayleigh number increases, like this. On the other hand, in the supercritical permeable case, the strong large-scale fluid motion with length scale of order H leads to the significant temperature fluctuation in the bulk region. As a result, RMS temperature scaled with delta T. And in the Navier-Stokes equations, the effect of the viscosity on the vertical velocity would be negligible in comparison to the advection effect. So the balance of the advection with buoyancy term leads to this velocity scale. And in the bulk regions, the RMS vertical velocity is scales with this velocity scale in the supercritical case. So in full regions, the velocity scale scales capital U, and the temperature scales with delta T, suggests that Taylor's energy dissipation law and the ultimate scale, meaning that the energy dissipation rate and the wall heat flux are independent of kinematic viscosity and thermal diffusivity. Also, the heat transfer is on the wall is dominated by the thermal conduction. Okay, let me summarize my talk. We have found the three-dimensional state solution to the Boussinesq equation exhibit multi-scale coherent structures, reproducing structural and statistical properties of convective turbulence. And this exact coherent thermal convection represents classical scaling between impermeable and ultimate scaling between permeable. And classical scaling is attributed to the vertical velocity fluctuation of this velocity scale corresponding to the small-scale thermal plumes in the thermal conduction layer. On the other hand, the ultimate scaling and Taylor energy dissipation law can be achieved through large-scale fluid motion with the length scale of h leading to significant velocity and temperature fluctuations of order u and delta t, even in the vicinity of the world. Okay, that's all. Thank you for your attention.
Thanks very much for this very interesting talk on Rayleigh-Bénard convection. So are there any questions? So this transition between the regular scaling and the ultimate scaling is observed. So here through the change in the permeable boundary condition. And recently there was in the team of Basile Gallet, they also found the ultimate scaling, but with internal heating rather than like, which also included maybe change of boundary conditions. Do you think that those works are related somehow?
The classical scaling regions, the transpiration velocity is weaks, and the ultimate scaling regions, so these particular transpiration velocity is enhanced in the disease. So this in the vicinity of the world, so this transpiration velocities induced inducing these transpiration velocities leads to the ultimate scaling, and the classical scaling regions, this transpiration velocity is weak, and so internal heating case. Yeah, so in the permeable on the permeable walls, so
excuse me.
Okay.
So may I say something? I'm Genta Kawahara, and my Dr. Motoki is my my colleagues, and of course, as you mentioned, we see the ultimate scaling in case of internal heating, but in our case, the heating mechanism is completely distinct from that. So I may say that the mechanism for the onset of ultimate scaling in our system is largely different from theirs. Thank you.
So from Subharthi, which is the condition of permeability related to the wall roughness effects?
I think so these permeable conditions directly related to not directly related to the wall roughness effects. This difference there is a difference. The wall permeable walls is differ is rough walls. So in the rough wall case. So in the rough wall case, the ultimate scaling can have been obtained, but so in the roughness case, the ultimate scaling is achieved by the limited Rayleigh number regions. So the roughness element size comparable with the thermal boundary layer thickness. So on the other hand, our permeable case, ultimate scaling is attributed to the transpiration velocity on the permeable walls. So this ultimate scaling is not limited, so is sustained at a higher Rayleigh number. We believe that. So this is a difference.